But it's my great pleasure to be able to introduce Mario Hofmann and also Yaping Hsieh, their team. They work together, and this is going to be an interesting seminar because it'll be pre-recorded. And just so everybody knows that if you have questions, you should put them in the chat, and he's going to be watching his own talk. And if you ask questions of yourself, I don't know how that works, but I think that yeah, we'll figure it out. Mario and Yaping, they work in this rapidly expanding field of 2D materials. And so I guess Yaping is focused on the synthesis, and Mario is focused on applying them and exploring some of the physics. And they're very interested in not only the sort of mainstays like graphene, but also new classes, discovering and developing new classes of materials and applications in a variety of areas, optoelectronics and sensing, plasmonics, and but I will let Mario hit play, or maybe Kerr is going to hit play, and we can take off in our seminar. So thank you for coming. I really appreciate you being here so late in the evening.
No, thank you for coming so early. So it's going to be an interesting experience. You're going to see me pre-recorded with better hair, and especially my wife is going to take the heavy lifting of giving a more interesting talk. So I'll be online, and I'll take questions afterwards. But also, if you have questions during the presentation, please chat with me, ping me. Thank you.
Okay, I'm going to go ahead and play.
Where'd we go?
Is there no audio?
There seems to be no video either, but he's holding his hand up like, give me a second.
So welcome to Taiwan. Thank you for your interest in 2D materials. Now let me tell you more about it. Let's go. I would like to introduce a little bit about 2D materials in future electronics. And so this is Taiwan. We have famous bubble milk tea, and we have very high mountain and 101. It was the tallest building in the world, and now it's like 10th. And so semiconductor industry is a very important part of Taiwan. It's like a quarter of our GDP currently. And so semiconductor is a very important research in Taiwan as well. So we've been trying to focus on the research on this area, and as the channel length getting smaller and smaller, it's getting a little bit iffy that how we don't like. They're starting to have problems with physics. Like for example, currently silicon itself is a 3D material, so the roughness by itself is too big that you cannot avoid the electron scattering effect. And so with the dimension getting smaller and smaller, the mobility is getting really, really tiny. Look at this trend that you can tell that when it's passed to almost 2 nanometer, that when the thickness is below 5 nanometer, the mobility is dropping like exponentially. And when it reaches that 2 nanometer, there's almost no mobility. That's why we start to introduce 2D materials, because it itself is made to be atomically flat. And so people has demonstrated it with like a 1 nanometer thickness, mobility of 2D material is much better than current other semiconductor thin materials. And the good thing is that currently the silicon is made into already 2D-like. And you can see this is how a current transistor works. And they made the silicon into like 5 nanometer thick and make into multi-layer stack way. And so that is it's a good thing for 2D material, because we just need to figure out how to grow our 2D material into that confined space. Then we will be able to replace current silicon CMOS already. And so that's why we work on confined CVD growth. And to go on with that, I think I probably have to introduce how CVD works first. And so CVD usually require a high temperature and some precursor, and we will need to some precursor that consists of the atom that is required to assemble into this hexagonal 2D shape, 2D material. So for example, graphene, we will need methane, CH4, as a precursor to decompose into carbon radical, and then assemble this carbon radical into hexagonal carbon shape graphene. And so I will start with our study on confined space, and because that's required for integrate 2D material into silicon FinFET. And so before us, there is no one that actually studied the confined synthesis, and so we were like the first one to do so. So it was actually very hard. We don't know anything. So we first started with just putting a cap on the growth substrate and changing the gap and see what happens. And we found that as the gap getting smaller and smaller, the growth rate decreased a lot. I thought it's this one. Okay, sorry. The cap, as the gap decrease, the gap size decrease, the growth rate also decreased by a lot. And so by this rate, when we reach nanometer gap size, we expect almost nothing can be grown. So we were very kind of worried about that. And so on the other hand, we found that when the gap size becomes smaller, because the growth rate is really slow, and the 2D material can be grown into a very high quality material, because if you give time to grow, the defect itself can actually cure, and the defect level will be much lower than the general 2D material growth way. And so that's what we are seeing here. As the growth rate it becomes smaller and smaller, the defective level, which we label by ID-IG ratio, is also getting smaller and smaller. So the whole thing, the confined synthesis, the growth rate can be simply the growth rate here. So the growth rate here can be simply explained by how precursor is diffused into this confined space. So we found that the diffusivity is dominated is dominating the growth rate, and so it's also completely correlated to the gap size. And so we were wondering how come it's so slow, and so we did simulation and found that because it doesn't make sense to us, it's way too slow. We calculated every 1 million of the methane, the carbon radical, carbon precursor, there's only one carbon that actually converts into the graphene atom. So apparently we're using this very inefficiently. Every 1 million of precursor, a carbon that we put in, only one grown into material, 2D material. So we're wondering why. And so we did simulation, and we found that actually flow speed is the dominating factors. The flow speed of the molecule is very important to the growth rate of 2D material, because if you flow too fast, the material will get, before the molecule, the precursor got converted into useful carbon radical. If you flow too fast, it's already got pushed out. So there's no way the precursor can be grown into 2D materials. And so that's why what I'm showing here, which is the growth rate, the flow speed versus the growth rate. Actually, what I'm showing here is the carbon concentration versus the flow speed. And in the beginning, the flow speed is faster, and we try to flow really, really slow, and we found that there will be useful carbon radicals available around the sample. And so that means that in general, in general for open space synthesis, the efficiency of growth are very bad, are very low. And so for the growth rate of the 2D material, it consists of 3 parts. One is the transport, which means that how the precursor is got transport into the growth substrate. And the second part is the conversion. This molecule not only have to come to the substrate, but also it has to be converted into useful carbon radicals. And then these carbon radicals can react and be assembled into 2D materials. And so our simulation told us that the methane, the carbon precursor, it's the flow speed of the methane is solely dominating it's the dominating factor for the conversion efficiency, and so the growth rate. And so now that we understand that we just need to control the flow rate to be really, really slow, so we try to use ultra slow flow rate. And actually by using ultra slow flow rate, it also means we have to flow really, really little carbon radical, which is not so intuitive to us before, because before we always thought that the more carbon we put in, the more the graphene it will be grown. The more precursor you put in, the more it will be grown. But in our case, because flow rate is a dominating factor, so the less carbon you put in, the more you actually grow. So that's what we're seeing here. And so with 10 times less carbon that is put in, that we can grow like 100 times faster. And so with that method, we managed to not only grow graphene, but also grow 2D semiconductor material. What I'm showing here is WS2, and we can grow like 7 centimeter each wafer and 10 at once. And so this is very exciting, because currently tungsten disulfide is very expensive. It on the market is like 1 centimeter for $300 and $300. And so well, we can just score 10 minutes and we can obtain like a 10 wafer, and this price will be up to like will be up to $20,000. And so for the flexible substrate, like graphene, we can just basically just wrap it, because now that confined growth is not a problem. We can simply just wrap the whole material substrate, and we can grow whole row of the material, and that's why we can grow directly 10-meter scale of the graphene at once.
Now that Yaping has told you about how to integrate 2D materials, we should discuss about why 2D materials should be integrated into future electronics. And that is actually a hard question to answer, because 2D materials are competing with much more mature technologies. And to see how those stack up, the technology roadmap has developed certain metrics. And we see that in this metric, scalable production and compatibility of the technologies are only two aspects. And so how does 2D materials stack up in other parts? And unfortunately, we have to admit that it doesn't look very good in other areas. For example, when we are comparing the transistor metrics, we are expecting that we would need a low leakage current and a high on current. So that means that we basically have to find a balance between those high effective mass and that is required for tunneling, and low effective mass that is required for high mobility. And it looks like WS2 might be somewhere in an intermediate range that can satisfy both of those requirements. There is, however, one problem with WS2, and that is currently the mobility is not as great as expected. The mean free path of carriers in WS2 is pretty much what you expect from just extrapolating the mobility to deterioration of silicon towards nanometer scale. So there's currently no reason to use WS2 because it's not outperforming silicon. But that's because WS2 actually is fairly defective. And so we have introduced a new type of growth where we're providing a mediator to take the two precursors necessary for growing WS2 and improving their combination into the final product. We're using carbon because carbon would help in the reduction of tungsten oxide and stabilize the supply of suitable precursors. And the result is very promising. We see that we can generate very large grains of WS2, and these ones are indeed single crystalline. And if we zoom in, we find that we don't observe any lattice defects. And so that can also be shown by spectroscopy. Photoelectron spectroscopy shows that the WS2 has pretty much intrinsic, like a Fermi level where you would expect it, half of the band gap. And we can also check optics, and we find that the photoluminescence intensity of WS2 is orders of magnitude higher than for normal CVD growth. And if we're checking power dependence, we observe that it, even at low powers, has a linear dependence of emission intensity on excitation intensity. And that's a sign that there's less traps. Another way to check the decreased importance of charge traps is that mediator-assisted CVD has the same lifetime, like it's just a single lifetime, whereas other like materials grown by other processes have a fast decay and then a slow decay because it's getting trapped in trap states, and so that yields materials that are significantly better in optoelectronics. We're getting quantum yields that are near unity for mediator-assisted growth, whereas for both exfoliated and CVD-grown WS2, the quantum yield is much lower because of the presence of traps. We can translate that into electronic devices. Optoelectronic devices like photosensors are easy to do. They're just two-terminal. And we see that they're both very sensitive and very fast. So the ultra-fast response is an easy way for us to check that the mobility is probably pretty high, and the responsivity tells us that we're not limited by traps, like by saturating traps. So that means that we can kind of compete with existing materials in terms of quality. And so that's a promising direction. But the question is that really the reason we should integrate 2D materials because they're better? And also, are there other limitations that we should be aware of? And so the second part of what I want to talk about is playing to the strengths of 2D materials. Because we are currently competing on the terms of conventional CMOS. So we're looking into how do 2D materials behave on the playing field of conventional silicon. But is there something that 2D materials can do that would set them apart from both silicon and other nanostructures? And can that be applied to electronics? And we think that there one major aspect that is normally not being considered is interfacial ordering. So 2D materials have no dangling bonds, meaning that any interaction between adsorbents and the surface are van-der-Waals. And on the other hand, it has large-scale crystalline ordering. So there's weak interaction, and it's similar over long lateral scales. And so people have shown that you can use that to generate periodic nanostructures and to align materials on top. And so the first thing that we want to show is that we can indeed use a 2D material as a growth substrate. Because of this van-der-Waals interaction, that growth substrate is interacting much less than you would see for, let's say, silicon. And so in this case, we see that silicon grows clusters, whereas graphene would grow thin films, in this case of bismuth selenide. Interestingly, these films are not epitaxially ordered to the graphene surface. Instead, they are aligned with wrinkles that are forming on the graphene. So that tells you that the van-der-Waals interaction is weak enough that the grain basically can orient itself on the grain and then grow on the wrinkle and then grow out from there. And it also means that there is a wrinkle between adjacent flakes. In one direction, our wrinkles are only due to uniaxial strain. And so uniaxial strain is induced by transfer, not by the relaxation during cooling. And so this uniaxial ordering basically means that we're getting a material that has different electron transport and phonon transport across the wrinkles and along the wrinkles. So we're having an anisotropic material where both phonons and electrons are affected. And so that means that we can use that for seeing the anisotropic behavior of the thermoelectric performance. And we see that perpendicular to the wrinkles, we get a higher ZT because the phonons are more efficiently scattered than electrons, and parallel, the ZT is lower by about 50%. Also, we see that appeal of using an inert substrate because we can actually grow down to a single monolayer or 5 quintuple layers of bismuth selenide using graphene. So this is one application that you couldn't do with silicon, for example, growing ultra-thin, high-performance thermoelectrics. The other thing you couldn't do with other substrates is growing ferromagnetic materials. So recently, 2D ferromagnets have been demonstrated, but we're the first ones to grow single-layer vanadium sulfide, and we're growing it on both tungsten sulfide and on mica. Mica is a crystal that is whose structure is pretty conducive to epitaxial ordering of vanadium sulfide. Tungsten sulfide also has a comparable lattice structure. So both of them are producing epitaxial alignment. You can see that in the OM image. Within a grain, the vanadium sulfide grains, like within a tungsten sulfide grain, the vanadium sulfide grains are aligned. But more importantly, we see a very large magnetic response. In the MFM on the bottom left, you can see that the multi-layers of vanadium sulfide have a larger response than the single layers around it, but both of these responses are much larger than if it were a mica. And that epitaxial ordering gives us access to a ferroelectric response of vanadium sulfide, and we get ferromagnetism, ferromagnetic response. We get ferromagnetism up till room temperature. So one way of using 2D materials might be as a substrate for synthesizing other 2D materials. But we actually came up with another idea, and that is, instead of growing on top of a 2D material, how about we grow underneath of it? So underneath means that we're growing in the van-der-Waals gap that is being produced between a 2D material and its substrate. And so that means that there is a very narrow confined space, but as Yaping was explaining, diffusion goes even into the, diffusion proceeds even in these very narrow volumes. And so we can get chalcogen atoms in there, and then we're expecting that reaction would happen either in lateral direction or by the chalcogens reacting with the substrate. The substrate in our case is a metal, so there could just form chalcogen compounds that way. But we find that the presence of a 2D material is actually making the planar reaction or the diffusion sideways much more efficient than the interdiffusion into the substrate. In our case, we're using sulfur and copper, and we see that planar 2D crystal of copper sulfide is formed, whereas the copper substrate has a very sharp interface with that crystal. The graphene in this case is not visible in the cross-sectional TEM image, but we can see the presence of graphene from a diffraction image of the face, basically, the basal plane. And we see that graphene is not aligned epitaxially with the copper. So that's strange. The other strange thing is that we're getting hexagonal copper sulfide, and that's different from if we just grew without the graphene layer. So the graphene layer is doing several things. The first one is it's changing its morphology. It is making the copper sulfide flat. The other, as opposed to having clusters on the just sulfurized copper surface. The other thing is that if you use an untreated surface of copper without graphene, you get cubic phase copper sulfide. whereas you get a hexagonal phase copper sulfide with the graphene super layer. And so that means that the growth morphology is completely different. If we're growing for longer times, we only see that the flakes are getting bigger and thicker. We're not seeing that the roughness decreases or increases if we're going thinner, as you would expect for 3D materials. So it is a layered material, and it's growing layer by layer, but it can be grown thicker. This is very different from 2D materials, which normally just grow a single layer. And then once the either catalytic surface or the epitaxial attachment is completed, they will self-limit. They will not grow a second layer. Instead, we find that our thickness is following a diffusion law very well, and we can adjust the thickness pretty precisely, because every hour it only extends by about 5 nanometers. So that's the one interesting feature of using 2D materials interfaces for ordering. The other interesting feature is that the thermodynamic phase that we're observing, beta CO2s, is not supposed to be stable at room temperature. So we are doing these experiments slowly enough that we can assume adiabatic conditions, and we find that only over about 100 degrees we would expect beta CO2s to be stable, and it should transform into gamma CO2s under that temperature. But what we're seeing is that phase change is only happening around 140 Kelvin below the equilibrium conditions. So also we see that this is not an epitaxial, so it's not a quenching effect, and it's not an interface strain effect, because no matter how thick your CO2s is, we always see it forming the beta phase. And so this is interesting because we really don't understand what makes it stabilize in that normally unexpected thermodynamic phase. The other thing is that beta CO2s might be more interesting than gamma CO2s because it should have superionic conduction, and it also might allow us to use the phase change for, let's say, memory. This is not limited to sulfurization. We've played with different materials, iron sulfide and nickel sulfide, as well as copper selenide. And so copper selenide is forming, again, a normally unstable gamma CO2s, and it's forming atomic interfaces. But interestingly, because the sulfur is smaller than selenium, so it diffuses faster, we can actually get selenium crystals that are down to a single monolayer. So we're measuring in the presence of both graphene and a water layer about 1.6 nanometers. So extrapolating from there, we're getting that CUSE is a single layer if we're growing it short enough. This is exciting because CUSE has kind of unexpected properties. First, we're seeing it has a band gap of about 2 eV, which is interesting for optoelectronic devices like light emitters and solar cells. And it also has a fairly high Seebeck coefficient. So the thermal power and the ZT from that thermal power is about 1. So it might be interesting for energy generation or energy harvesting. So these are advantages of 2D materials and the ordering that they induce on materials that you grow on them. But there's one problem with 2D materials, and that is that even unwanted adsorbents are ordering. So we're getting adsorbents from all kinds of sources because 2D materials are very high in surface to volume ratio. So basically every atom is at the surface. And so adsorbents are coming from the environment or during processing. One of the main problems is that, especially for graphene, we have to transfer it. And so normally, and so we're getting doping. And so normally doping is not a bad thing. Doping is a mainstay of semiconductor processing because you can change the resistance of silicon, let's say, by introducing controlled amounts of dopants. But if we do that with graphene, we find that there is no control. we see that first the resistance goes down, and then it stays kind of constant, and then the resistance goes up with doping again. So it's not following, normal bulk semiconductors. The other thing that we're seeing is that this is not, even if we're keeping the same number of charges and like the same amount of charge transfer, we're seeing that depending on the etchant that we're introducing, we get different mobilities at the same concentration. So this is strange because up till now we always assumed that charge transfer was the only thing that would introduce scattering, but now we see that there seems to be another quality of charge transfer depending on the chemical that has an effect on mobility. And so we call these neutral scatterers because they are not depending on the amount of charge that you're introducing, but they seem to be depending on the type of etchant that you're using. And we find that the variation with etchant is about 6 in mobility. So that's much larger than the variation within one etchant that comes from random charge transfer. So we find that the etchant has a big effect on the mean free path of electrons in graphene. And this seems to be the shared mechanism. So it's just that that different etchants are decreasing the mean free path by different amounts. And so we're conducting Raman spectroscopy and statistical analysis of Raman data. We get maps, and we see that the ammonium persulfate has very uniform distribution of charge transfer. We can map out the charge transfer between graphene and adsorbates by Raman position. And so we see that it's pretty uniform for ammonia persulfate, whereas iron-based etchants have very non-uniform distributions of charge transfer. So you're getting these charge puddles of high and lowly charged regions. And so it seems that this is the hallmark of a bad etchant. It's not about how much charges they're introducing. You see APS is actually doping p-type pretty heavily, but it's introducing no or very limited heterogeneity in the doping, whereas iron-based dopants, especially iron chloride, is introducing a large range of doping, and so we're getting these charge puddles in bad etchants that are now not only messing up the mean free path, but they're also messing up the transconductance of our transistors. So because as we apply a gate, the additional charges can either stay on the graphene and modulate the graphene carrier density through the quantum capacitance, or they can go into the charged puddles. And so that is happening more at low amounts of quantum capacitance or low values of quantum capacitance. And so we find that it's affecting the transconductance more significantly at like close to the Dirac point, and even worse because these are like the charge puddles are mainly one type in a uniform matrix of another. So we think that this is heavily p-type doped in lightly p-type doped graphene. We find that they would more significantly affect electrons than holes. And so we're seeing this unipolar transport instead of the ambipolar transport that you would see in other etchants. So that's a bad thing that adsorbates basically are forming these clusters on 2D materials. But I want to point out a beneficial area of this, and that is to lithography. So currently lithography is using optics, and they use a step and scan technique to get high throughput and surprisingly high resolution. But if you wanted to push the resolution even higher, you would exponentially decrease your aerial throughput. So we instead are using this ordering effect for our advantage. The way that we're doing it is we're using fluorine as an adsorbent, and we're intrinsically having bilayer regions on the graphene. And so fluorine would interact with the exposed phase, but the graphene that is underneath the bilayer would not experience fluorine interaction. This is important because it stabilizes the fluorographene on top. Basically, it keeps it from volatilizing, whereas regions that don't have another layer of graphene underneath are volatilized by basically a kind of a zipping mechanism of the fluorine. Multiple fluorines get into a defect, and then they start breaking it from there. So we find that we can stabilize both the fluorographene top layer and the pristine graphene bottom layer if they're underneath one another. And so we use that as a hard mask. And a hard mask means that we can now use graphene as a protecting layer for the silicon underneath. Not just silicon, but any kind of material underneath. And so regions that have double layers of graphene would be protected during dry etching, whereas regions that have only a single layer would get removed. And so we show that before you have these two layers of graphene, and afterwards only the bilayers remain. And so the features that are covered by both of them could have very sharp corners. And so we've used that to produce features that are 5 nanometers in size. And so this is done by simple optical large-scale lithography, but we can generate this with very high throughput and very high resolution. The last part that I wanted to describe is a strange effect that we're seeing when we're ordering water on or in between 2D materials. So water is forming layers on any kind of surface, and normally these layers are fairly thick. Water is not self-limiting in its adsorption. But what we're doing is we're applying a mechanical force between 2 layers of graphene, and so we're squeezing out the excess water. We thought we squeezed out everything, but we're going to get back to that. So we're squeezing out water, and by nano-electromechanical drum structures. So both of the layers are getting in contact, and they're forming this very tight interface. What we're observing, however, is that we're getting a ferroelectric behavior. We're seeing the change of the static dielectric constant with voltage, and so it's a sign for like an increase in polarizability. And we also see that as the switch closes, the static polarizability increases. So it gets harder to reorient the molecules, which means that there's probably still water in there, but as we squeeze it, it doesn't have a lot of space to rotate. And so this is important, or this might be the indication of why we're seeing a ferroelectric behavior, because the water does have a dipole moment, right? It's just that normally you're not forming crystalline ice. So we're forming this layer, and it has a ferroelectric ordering. And as we introduce more water, we see that both, like, the distance between the layers gets larger. There's more water inside, and as we get towards a bilayer of ice, we're getting a decrease in our polarization. So that means that we probably produced a ferroelectric phase of ice between those 2 layers. It has been previously reported on extremely controlled surfaces in ultra-high vacuum, but ours is just operating in ambient. Not only that, but it's a very robust process. You can turn off the power, and it retains its orientation. We can use it kind of as a memory, because the ferroelectric response can be modified by a field, but then you can turn off your power. And this is only possible because we're combining mechanical and ferroelectrics. So we're making a new kind of mechanical switch, because normally your mechanical switch would have to get in contact and release at the same at the same polarization of voltage. So it's a unipolar behavior. You set at a high voltage, and then as you release, you reset it. So there is no mechanical memory, because if it sticks together at 0 voltage, then it will simply not come off. But in our case, because the ferroelectric can provide reverse polarization to the applied field, we can get repulsive forces. And so we are observing that we can get mechanical switches to reset. So we have a bipolar behavior that is necessary for memory. And so this is not just a ferroelectric memory, but this is a mechanical memory. It's not only distinguishing between on and off, because now ferroelectrics and mechanics are working together. You're getting memoristive behavior. Basically, your performance depends on history, like a memoristor. In our case, it means that the voltage at which reset occurs depends on the previous highest voltage that we used to initialize the ferroelectric. And so it's very linear over a very large range. So you can use that as a multi-bit memory. And we can also use it as like it's very reliable and very quick. So we can switch it thousands of times without deteriorating its performance or deteriorating the quality of the graphene. So I hope that in this talk has given you a little bit of insight into why we're so excited about 2D materials, because they are promising as components for future electronics. They are having high performance. We can now adjust the thickness and other aspects of their morphology to make different kinds of 2D materials out of the same chemicals, basically. And they are inherently integratable with silicon technology, which is different from other nanostructures. There is an effect of adsorbate ordering that provides both a challenge and an opportunity for future devices. It's a challenge because now it's not enough to just control the concentration of impurities, but it also provides opportunities to make new types of 2D materials, or to make new types of hetero interfaces between 2D materials and the outside world. This research is still very much in its beginning, because we are confident that 2D materials can help with electronics, but we don't know which 2D materials will make the race. We are currently hedging our bets by just looking into many types of 2D materials, but in the end, we will have to do the legwork and put all of them into transistors and see which one comes out on top in terms of mobility and leakage current. Also, we are currently learning from semiconductor industry as to which processes they are allowing inside their fab, because currently our fabrication, our deposition, all these things are kind of incompatible with a clean room. And so there is still a lot of engineering work to be done on how to get the growth towards the requirements from industry. And the last thing that could drive future research into 2D materials would be a killer application, something that has less competition. And so maybe it's using their mechanical properties or properties that haven't even been discovered. With that, I would like to thank you for your attention and thank our group for making this all possible. Thank you.
Well, that was great. Thanks so much, Mario.
Yeah, thank you. This was great. I think this worked out really well, actually. I mean,
yeah, I was surprised. I had not watched myself.
So, well, maybe we can take other questions from the audience. I have a lot of questions, but we're also like, my group is going to meet with Mario and maybe Yaping later on this week. So we'll let other people ask questions with priority.
I'll ask a question.
Yes.
Hi, Mario. I'm Susan Fullerton. I work with KA. And we have an active collaboration right now with some folks at Penn State who they create these two-dimensional metals in a confinement approach that I think is analogous to what you're saying here. And they kind of the sealant on the top is a layer of graphene. Right. And the thing that they find is that it kind of self-heals, like after they grow the 2D metal, then the graphene grows back again to fill in those holes that they created to allow the 2D metal to intercalate. Do you have something analogous for these 2D confined structures that you're building?
So yes and no, it's a little bit different. So as you were saying, basically what they're doing is intercalation, and they've done very pretty work for intercalating gallium in there. So there's no chemical reaction happening. It's a physical absorption process, basically. So we're seeing that we can actually conduct chemical reactions that fill the pores or that close the pores. So one thing that I haven't really gotten into is that copper selenide we can make into single layers, but copper sulfide, because sulfur is smaller, the diffusivity is higher, we have trouble. It's like 3 or 4 layers. And so we find we can actually close the passages where the sulfur would come through by selenium. So we would dose sulfur and then we would dose selenium, and the selenium would close the pore, and then it would allow the sulfur to more homogeneously distribute and form nicer and thinner layers. So it's not that we're not healing the graphene, but we still manage to close the pores, because we think that it's because the pores itself are reactive enough that you would just, the dangling bonds of graphene basically would stick to anything. We had seen that before. Depositing aluminum oxide would close these nanometer-sized defects in graphene, and then it's inert. So I would say that graphene currently is not inert. That's why stuff goes through, but it's fairly easy to render it inert, just because the openings are reactive. So they like to clog.
And then the etchant that you're talking about, and you were showing the results of the impact of the etchant. Is that the etchant to get the holes before you actually, right?
The etchant we think is mild enough that it should not react with graphene. It should not deteriorate it, at least for graphene. For other TMDCs, probably the etchant is introducing additional holes. But we think that the holes are in the graphene to begin with. They are holes that are at the grain boundaries, because we're growing like polycrystalline material. We're estimating the size to be a couple of nanometers, because we used ALD to clog the holes, and we need about a nanometer to just have enough material to prevent additional stuff to come through.
I see. So the etchant is afterwards to reveal the 2D, to reveal the thing that you grew.
It removes the graphene from the copper, from the gross substrate, or from the substrate you put it on.
I could be wrong. I can't remember now. I feel like for the 2D metals, I think they do have to like blow some holes in it. Or if the step height is high enough on the silicon carbide on which they grow, then you have an entry point, right there where the graphene is discontinuous. But don't quote me on any of that. Anyway, thank you for your talk today. It was really interesting. Oh, sorry, Mario, you were still talking.
We have blown more holes into our material, and it helps. So we can break the graphene pretty easily. We're using ozone, so that just oxidizes the graphene, and it makes it much easier. The problem is you actually don't want it to go too fast, because then it gets thick and it gets into clusters.
Right. Very neat, very neat. Thank you, Mario.
Can I ask a follow-up question?
Sure.
So I think you mentioned that you can control the thickness of the new material you grow. Is it only like in between the graphene and the metal, or is it also on top of the graphene?
So we find that, that's a good question. We still don't understand what's happening really, but what we find, so in the simplest case, we find that it only reacts under the graphene. So when we're putting sulfur, it's forming elemental sulfur on top of the graphene, but copper sulfate underneath. So that, sorry, copper sulfide underneath. But that's only the simplest assumption. When we wait long enough, we see actually the copper coming out of the graphene, which is weird because we're using about 300 degrees C. That should not be enough to get copper to move. Copper's melting point is way too high. So we don't understand why copper would form micrometer thick layers within a couple of hours. So if we dose it well enough, we only get it underneath. And so that's what I was showing today. I left out the messy part, but the messy part is pretty cool because if it's really possible to grow these beta phase CO2s at micron thickness, it might be useful because it's a superionic conductor. It's a very strange material.
Great, thanks.
Well, I think maybe this is a good time to wrap it up and to thank you, Mario and Yaping, and really this is really great, and I'm looking forward to more discussions with you. Yes. And I think we have something scheduled. I think I had to. Well, I have a group meeting right now, but
okay.
That's I'll get it. First thing I'm going to do is remind them of our meeting, which is 8 p.m. our time this Sunday. And right. I think that's like Monday would be
Monday
like
night.
Monday morning. Monday,
really
yeah.
Perfect. It works better that way because it's 13 hours off. So for us, it's already.
Right. Yeah. So thank you again for wonderful, really exciting work, great presentation. And yeah, I guess. Yeah,
also,
thanks for
just as interjection, if any of you is interested in some of the 2D materials, you saw that Yaping was showing that we're growing now basically 5-inch wafers at a time. So if you just want to play around with WS2 or something, we have tons literally lying around. I think we sent like 1 wafer to Jeremy. I think from the same stack, we have like this much still left.
Oh, wow. Oh my God.
You just want to see WS2, hold it in your hand. Just
yeah, it was amazing. Yeah.
Well, I might take up your offer on it. Okay.
It's kind of like a doorstop for us now because we're interested in making it, but then we don't know what to make out of it. So please do.
Okay.
Yeah, I was not expecting you to spend so much. It was like, oh, what is this? Is this like a packaging? It's like, no, this is the.
That is the actual material. And so yeah, Ping was telling you it's about $20,000 US, I think, right there.
Wow.
So
amazing.
Thank you very much for having me. And I'm looking forward to talking to Jeremy's group on Sunday. I didn't realize it will be your group. Do you want to reschedule? I don't want your group to
well, I'm going to make it, I'm going to invite a few people. We'll see how many people, okay. We may keep it a little bit smaller, but yeah, but some of the key people will be there.
Awesome. So see you then.
Yeah.
Thank you.
Thank you, Mario.
Okay, bye-bye.